Okay, so the recording has started. We get to the second part of the third summary lecture of the part 2. And just before we begin, we can have a short recap on what we did last week. So if you remember, we did look at what electric flux is. So it is actually multiplication of the electric field that passes through a certain area. So you multiply the area by the electric field at normal angle. Then you get the electric flux, and it means the total number of, you can consider it as a total number of the electric field lines that are passing through a particular area that we can consider as electric flux. Then we discussed about Gauss's law. So before we talk about Gauss's law, we have to understand what Gaussian surface is. So any closed surface, so a surface that encloses a volume, completely encloses a volume, it's called Gaussian surface. And the Gauss's law states that the total flux through the Gaussian surface, through a Gaussian surface, is going to be proportional to the total charge that is enclosed in that volume. So, and that's given by the total charge divided by epsilon 0, which is the permittivity of free space. It's a constant. So in this diagram, you can see that only Q1, Q2, Q3 will contribute to the net flux through these closed surface, whereas Q4 and Q5 will not play any role in the net flux. Okay, so we can apply this Gauss's law for finding out what the electric field is going to be in insulators as well as in conductors. You have to make use of the geometrical symmetry nicely. Then you can easily work out what is the best. What is the most suitable Gaussian surface that you should be using for that particular problem? So in this case, because your charge distribution, for instance, is a sphere, then in this case, it would be best that you create a spherical Gaussian surface, and so on. So, and for the conductors, you also need to make use of the fact that inside the conductor, the electric field is 0, and all the charges will accumulate all the net charges will accumulate on the surfaces of the conductor. So in this case, there are in this spherical shell conductor, there are two surfaces, one inner, one outer. So the charges will somehow distributed along or over the surfaces of these conductors. And in order to find out exactly how much charge gets drawn to the surfaces, two surfaces, you need to use Gauss's law, shown in this example. So, any questions up to this point? So this is what we have last week. What we have done last week. Okay, so I will move on to the next topic, which is on electric potential. Okay. So just before we begin, we have to cover two topics today. One is on electric potential and the other one is on capacitance. So I'll try to do these quickly. Okay. So electric potential, the definition of electric potential. Let's look at that. So when you have a charge Q0 in an electric field and you wish to move this charge from one place to another place, let's call it from A to B. Okay. You need to put some energy into it. Okay, and how do you calculate that energy? Work done is force times distance, if you remember from elementary physics. And how do we calculate force? The force that is required to move a charge is the size of the charge multiplied by the electric field, right? And then the distance A, if you are moving this in uniform field, then you just multiply the distance that you have moved, AB. AB is the distance that you have moved. And that will give you the work done in order to move this charge from place A to place B. So let's say electric field is flowing in this direction with these arrows, and then your charge is positive charge. Do you need to put in energy, or do you actually get energy out of it? You actually get energy out of it, because if you just leave it without putting any force, it will, of course, it will move in the direction of the electric field if this was a positive charge, right? So in which case you are gaining energy in this case, right? You're gaining, the charge is gaining energy, or it is losing potential energy, or it is gaining the kinetic energy, for instance. Whereas if it was negative charge, then in order to place this Q0 from place A to place B, you have to apply the energy. You are losing the energy, or the charge itself is gaining that potential energy from you, right? And this is where this minus sign is coming from. The negative sign is the fact that when you are moving in the same direction, when the charge is moved in the same direction as the electric field, or the positive charge is moved in the same direction as the positive field, then you are actually losing the potential energy, because you have even if you, without you moving it, it would have moved that way, but you actually moved it by yourself. So then you are losing the potential energy contained within this the potential energy that the charge had. Whereas if it was minus, if the charge was negatively charged, or you're moving against the electric field, then you'll be gaining the potential energy. So this is where that minus sign is coming from, and this is for uniform field. And in the case of non-uniform field, instead of just doing a simple multiplication like this, you need to take the line integral. So if it was moving in certain path that is, and then the electric field along that path is not uniform, then you have to calculate the electric field, multiply the electric field and the small element of that path all together, and then add them all together from A to B, and multiply by the size of the charge itself to get that work done. Okay. Now, then the definition of electric potential becomes that what is the energy required to potential energy per unit charge. So you calculate the energy per the potential energy that is required to move from A to B, or potential energy gained from A to B, or energy that you put in. And then you divide that by the size of the charge Q0, and then you get the voltage, or the electric potential, which is often called, measured in units of volts. Okay, and likewise, this would be, so if knowing that the potential energy of the charge is given by this equation, then because this is then the electric potential is given per unit charge, you just divide it by Q0, and then the electric potential moving from A to B is going to be given by this equation. And for non-uniform field, it's going to be given by that equation. We just remove Q0. Okay, so one of the properties of electric potential is you can draw so-called equipotential surface. That means a surface having the same electric potential. So let's assume that we have an electric field that is uniform, and it is coming in just all in one direction from top to bottom in this case. And then we can kind of say that at these surfaces, or I mean, I've drawn it with just a line, but you can imagine that the entire surface extends from coming out of your screen and also going into your screen, whereas the electric field is all going in this direction, also extended through the in and out of your screen. Okay, then in that case, you can draw this dashed line plane. This is going to be a plane, which is where all along this plane, your electric potential is going to be all equal, and that's called the equipotential plane. Okay, and so that line is, or that surface is going to be equipotential surface, this is going to be also equipotential surface. And that one also is going to be an equipotential surface. Of course, between these three, the electric potential is going to be different, but just on that surface itself, if you just play along that surface, you will not have gained or lost any electric potential if the charge was moving, if a charge was moving between them. Okay, so this is the case for electric field going in a single direction. Whereas if you are talking about like a electric field from a single charge, then we understand that the electric field is going to be pointing radially outward. So you're going to have a kind of a spherical equipotential surface, because you see, if we have a charge here, then we know that the electric potential is going to be equal along those surfaces there. Okay, so this is how we can draw the equipotential surfaces for a single charge. Okay, so from this picture, what we know is that the equipotential surface is always 90 degrees to the direction of the electric field. And when we try to move charge along the equipotential surface, so let's say I have a charge here and then I want to move it to that point there, it requires zero work done, okay? Because you're not gaining any potential energy, you're not losing any potential energy by the charge is not gaining or losing any potential energy. So because it is not moving against nor in the direction of the electric field. If it was moving in the direction of the electric field, it will be losing the potential energy. If it was moving against the electric potential, electric field, and then it will be gaining the electric potential. So it will be gaining the potential energy. Then, since we know that the electric potential is given by the line integral of the electric field from the point A to B, so this is how much the electric potential has been increased or decreased when the charge was moved from A to B. This is how you calculate it. This was from earlier slide. Then, when we know the electric potential, then we can also obtain what the field is going to be. But in order to do that, we need to do the inverse of this integration, which is differentiation. But because the potential will be different in any point on space, in a three-dimensional space using the coordinate x, y, z, then in order to calculate the electric potential, you need to do so-called partial differentiation is that you differentiate with respect to only x in this case, and then consider any function, any y and z terms to be constant. Okay, x and y and z to be constant. This one, you take derivative with respect to y, and then consider x and z to be constant. And then this one, of course, then that means you take z to be you take the derivative with respect to z, and you take x and y to be the constant. So in this case, here is v that is only a function of x. So when v only changes with x, then in this case, v doesn't change with y, v doesn't change with z. So in this case, we just need to take the derivative with respect to x. And when you do that, then you can see that at this point, the electric field is going to be zero, because this is where you have the derivative going to zero in this point. And then in this case, you're going to have the electric field that is positive, because in fact, the gradient itself, the slope itself is negative, but because we need to negate the sign, to get the electric field from the potential. So then it's going to be positive electric field. And that means the field at this point electric field at this point is pointing towards the positive direction, positive x direction. Okay. Whereas in this case, the electric field is now pointing towards the negative direction, and negative x direction. Okay. And so from the function of the electric potential V as a function of x, you can easily calculate the electric field. As I said, we can quickly look at an example. So let's say we can describe electric potential at point x, y, z by this equation. Okay, so if we know what x, so we in our three-dimensional space, if we know the coordinates of x and y and z at certain point there, how do we calculate the voltage? We use this equation. Okay, in this case, in this specific example, then how can we calculate the corresponding electric field at point 333? So x is 3, y is 3, and z is 3. Now we want to calculate the electric field at that point. So we need to use this approach. So we first need to differentiate with respect to x. We differentiate with respect to y. We take the partial differentiation with respect to z. So in order to get the ex component, the x component of the electric field, because electric field, remember, electric field is a vector quantity, so we must have x, y, and z component, whereas the electric potential is a scalar quantity, so it's just a single number, right? It's just a single number at that point. Okay, so we're trying to get just a single from just single number, we try to get three components, and in order to do that, we need to take this partial derivative. So we take we differentiate this with respect to x. This is a partial differentiation, and with the partial differentiation, you have to consider in this case z and y to be y and z to be constant. So I didn't do we treated that to be constant. That's just a constant. So when you do the differentiation, we remove that, and then here you just take the differentiation with respect to x, and that becomes 6x, and then you put the negative sign, and then at that point it was asking the corresponding electric field at point 333, so you have to substitute 3 and 3 there, and then you get this number. You do the same for the y component, but here of course you differentiate with respect to y. Here you differentiate with respect to z. So this is how you do the partial differentiation, and you can get all three components using this approach. And then you can say that our electric field, the x component of our electric field is going to be minus 54. The y component of our electric field is going to be positive 54. And then the z component of our electric field is going to be 135. So is this part clear? Do you have any questions on how to calculate electric potential? I mean, how to calculate electric potential, we'll have a further example, but at least how to calculate the electric field from the electric potential. If you need to do some practice, I think your tutorial question number 3 in this week's tutorial question is on this part related to this. Okay, so here before we talked about how electric field creates electric field radially outward, a single charge, and then that also we were able to draw the equipotential sphere along that around that charge, and then that means also we should be able to calculate the electric potential due to that point charge. Okay, and that is given by this equation. So it simply depends on the size of the charge as well as the distance from that charge. Okay, and one important factor that we need to remember is okay. So here is how it would look like. So let's say you have a point charge here. At this point, r is equal to 0. Then further away you move out, then your electric field is going. Electric potential is going to decay with the inverse relationship with R. And if it was minus, if the charge was minus Q, then of course it would be also declining like that, but it will be negative potential, as you can see. And then the electric field is, of course, with the negative charge, it will be in the direction towards the charge as well, while the electric field would be going radially outward for a positive charge. Okay. So what does this electric potential diagram tell you? Like, if you placed a charge at origin, meaning at zero, and then you try to place another very small positive charge closer to it, then from infinitely far away, you try to place that charge next to it. How much energy you need to supply to that charge in order to place that test charge, we call it. Test charge is a small Q0 that's coming from infinity. How much energy you need to put in order to place it at that point. Let's say at that point, then you just need to read it off that value there. If that charge in the origin was plus Q. Okay, so this is what electric potential created by a single point charge means. Okay, and again, I try to emphasize that the electric potential is a scalar quantity. Why is it a scalar quantity? Because if you remember, it was the energy per unit charge, and we all know energy is a scalar quantity. There is no any direction involved with the energy, right? So then the electric potential V is a scalar quantity, and it only depends on the distance from the point charge. I mean, it also depends on the size of the charge. So that's just for one charge. Now, what if we have two or more point charges? Then you need to do a sum, algebraic sum. Because now you remember this is not a vector quantity, V is not a vector quantity, so you can just simply add them algebraically. Of course, if one charge is positive and the other one is negative, you need to subtract them. So if you had two charges, then it will be, sum of the two terms, three charges, sum of the three terms, and so on and so forth. So it should be fairly simple. Just algebraic sum of scalars. So we can take a look at this example. Let's say we have two charges. One is small q and the other one is big Q. So that's a 2-point charge system. And we can then calculate, we try to calculate the potential difference between A and B, right? Potential difference between A and B. So in order to do that, how do we approach this problem? So you need to calculate the electric potential at A, point A. And how many charges are affecting the electric potential at point A? There are two charges. So you need to calculate the electric potential due to the small q on A and calculate the electric potential due to big Q on A. And then you then add them together. Okay, so this is what I did. Electric potential was given by the Coulomb's constant times the size of the charge divided by the distance. So due to this small q is going to be that on A, point A. And then due to the big Q is going to be Q divided by A plus B, because the distance from A to big Q is B plus A, right? That's the distance. So when I do this calculation, then I get minus 114 volts. Why do we get minus? Because that's both Q and Q are negative charges. And then at B, you need to do the same. You need to do the same, but this time now the distance from the small q to B is going to be A plus B, whereas the distance from Q, the big Q to B is going to be just A. Then you see that you get this number, which then the potential difference between the two means the difference in the voltages between the two, you get 12 volts. Okay. So if you have 3 charges, how would you do it? You would need to, again, have another term added here, which is like another Q there, and then you get the distance, and so divide that divide the charge by the distance and then multiply by KE2. So as you have more and more charges, you need to continue to add and add on, right? Any questions up to this point? Okay, then I think we can move on. So the electric potential we were talking about is like if you already have a charge, how much energy is required in order to bring in another charge. This is how the electric potential is related, right? Because the existing charge already produces electric field. Now you need to move another charge which will react to that electric field. You need to bring it from very far away. Now you need to bring it close to that already existing charge. You will have to apply some energy. You need to give some energy to it, or you gain some energy from it too. Okay, depending on what the sign is. Okay. So this is what electric potential was about. So now basically we can actually calculate how much energy is required in order to assemble a system of charges. Okay, so let's just talk about assembling one charge. There's nothing else in this universe. There's just one single charge that you want to place it in some location in the space. Okay, how much energy is required? Is there any electric field existing already? No, there are no any electric field because there's nothing. The space is void, right? And then you bring in that charge. There's no any forces that is repulsing it from bringing it there, or there's no forces attracting it to bring it to that point there. Okay, so placing the first charge, the very first charge in the universe, it requires zero energy. You're not getting any energy out, you're not losing energy. Okay, so there's no energy required to assemble 1 point charge in the universe. Now, so that charge is already there. Now you want to bring in the second charge. How much energy is required? How much energy is required? So if it was this Q1 is an already existing charge, so it will create some electric field, and then you have to bring this from very far away, infinitely far away. So when it's infinitely far away, the electric field at infinitely far away from Q1 is going to be zero, right? So at that point, you don't have any force, either attracting it or repulsing. But as you get closer, as you move this charge closer and closer to Q1, then the effect of this, the force acting on this, acting on Q2 due to the presence of Q1 is going to increase and increase, right? Because you understand the Coulomb's force. So in order to move this, you either will require energy or you are actually gaining energy. If it was attracting force, you're actually gaining energy because this will be attracted with a stronger and stronger force. Whereas if these were two charges were of the same sign, then you would need to put more and more force to move towards closer to it. So in order to calculate the energy required to assemble these two charges, then you would need to multiply Q1 and Q2, the size of the charges together, and then the distance between the two. Okay? But this actually comes back to the very idea of how this was defined. So this is the charge per the electric potential per unit charge, meaning if we already have one charge, and then in order to bring in a test charge, how much energy is required? But how much energy is required per unit charge of bringing it in? And then now we actually apply that, and we are bringing in that charge. So you just multiply that electric potential of Q1 by Q2 to calculate the energy required to assemble these two charges into an empty space, let's say. Okay. Of course, then we now have we can apply the same logic to calculate 3 charges, and the equation is given by this. Okay. So first, of course, bringing in Q1 requires 0 energy, but in order to bring in Q2, you need to apply energy about that is proportional to this much, and then in order to bring in the third charge, then this has to it has to provide the energy required to bring in the third charge is going to be the energy that is required between these two systems and plus these two systems. So that's why we have that and that. And then if you want to have more and more charges, then in order to require energy required to assemble many charges is the sum of the energy required to assemble every pair of charges. So you need to look at every pair or all possible combinations of pairs. Right? Any questions? So we did discuss about how to calculate electric potential due to a system, multiple point charges, right? Due to point charges, multiple point charges. Then you can apply the same logic to calculate the electric potential due to a continuous distribution of charge at point P. So let's say this blue solid is a charge distribution over some sort of volume. Then in order to calculate the electric potential at P, due to all of these charges, a continuous distribution of charge, you need to do a volume integral of the entire thing, taking small fraction of these volumes, small volume fractions that has some charge dq in it, and then you need to add them all together, the small elements, to which translates to doing an integration over the entire volume. Then you can calculate the electric potential at P. Again, this dV, which is a small fractional electric potential that is coming from this small charge element dq up here, that's a scalar quantity. So you don't have to worry about in which direction this potential is directed towards, because there's no direction, of course, it's just energy per unit charge. And then that also means this integration, when you do the integration, you don't need to worry about adding up all the vectors. It's just going to be a scalar sum. So we can take a look at this example of charge distribution, continuous charge distribution, calculating the electric potential. Okay. So the charge of uniform density. So this is a uniform density rod. It has 10 nanocoulombs per meter. So it's a line charge density. It's distributed along the x-axis from 1.5. So the road extends from 1.5 to 4. That means the length of the road is what? It's going to be 2.5 meters. What is the electric potential relative to 0 at infinity? So why is it 0 at infinity? Because always you have single charge, and then if you are very, very far away, then you don't need any energy to place that, or you only need very small energy to place that another test charge at very far away distance, right? Because the effect from this charge is going to be very small if you are far away from that charge. And infinity, if the distance itself is infinity, then the energy will be zero. So that's actually what we call absolute zero electric potential. Okay. So what is the electric potential relative to zero at infinity at the origin? So that means, like, at this point, this is the origin, x is equal to 0. At that point, what is the electric potential? That means if I had a test charge that is located at very far away, how much energy do I need to put in order to place that charge over here? That's what it means by this question. What's that asking? So in order to calculate the electric potential at that point, we need to formulate a small potential element at distance x. So this x is going to be changing from, of course, 1.45 to 4.0. But let's assume that this x is just right at this point here. Okay, and just arbitrarily somewhere in between where the rod is. And then at that x, within this small element dx, there's going to be some charge there. Okay, so let's call that charge dq. So dq, in fact, is the small amount of charge that is located at this position x within the length dx. And the electric potential due to that small element dq at origin is going to be dq divided by x times the Coulomb's constant. Then you get that small contribution from that red highlighted part at the origin, the electric potential. Okay, so that's going to be our dV, the small element dV. Okay. Now, also, we know because we have a uniform charge density, then the amount of charge, small charge in that small element dq is going to be the lambda times dx, where dx is that small element, the distance of the length of that small element, and you multiply it by the line charge density, and you get how much small charge is going to be located within that dx. Okay, so then you can substitute, of course, that in here, and then you get ke dq x. Now, what you have to do in order to calculate the electric potential at this point is now you have to integrate the dV over 1.5 to 4. Okay, x of 1.5 to 4. So from A to B, So substituting that in, and then you're taking the integral from A to B. Then you get to this is after the integration, and the limits are from A to B, and you substitute this in, then you get 88 volts. So that means with this continuous charge distribution that looks like that, and at the origin, the electric potential is going to be 88 volts. That means if you had a Coulomb of charge, very, very far away, it would require you to put in 88 joules to place that charge at the origin here. Got it. How are you doing? Any questions? Okay, so that was the electric potential for insulating or continuous charge distribution in insulating medium. In a conductor, the charges, as we already covered, the charges can freely move. They can move around freely. So if there is any electric field and you place a charge, the charge will immediately move. So charge will not stay there. Whereas with the insulator, why all these problems you have to distinguish between the insulators and conductors is because in insulators, even if the charge is under some electric field, it will not move. It will still stay there because they are not free to move. Whereas in the conductors, they are free to move. So if you place a charge under some electric field, it will just move out of it. To where? To the surface of the conductor. That's what we learned last time. Okay. So conductor at electrostatic equilibrium means now the charges are no longer moving because when I place a charge inside an electric field and then when it moves, it's not electrostatic equilibrium. It's because it's not static. The charges are moving. But after everything has moved and then all the charges are now located on the surface of the conductor, now we can say it is electrostatic equilibrium. And electrostatic equilibrium, we know that the electric field is zero inside, the total zero inside, and we use that to apply the Gauss's law in conductor. An electric field just outside the conductor is normal to the conductor surface. That also I think we discussed last week. So that means, because if you remember the equipotential surface, equipotential surface is where electric field is 90 degrees to the surface. Okay, so if the electric field just outside the conductor is normal to the conducting surface, that also means that the entire conducting surface is going to have the same electric potential. So it's an equipotential surface, in fact. Okay? So it's an equipotential surface, and in fact, also the electric field potential everywhere inside the conductor, including the surface, is going to be constant. Okay. So if I was to draw a spherical a spherical conductor that looks like that, we understand that the electric field and the charges, the net charges, all going to be residing on the surface of this spherical conductor. Then, and we know that electric field inside the conductor is zero. So it's going to be zero, but then electric field is going to, if you apply the Gauss's law, the electric field is going to be a finite number just outside the conductor. So it will shoot up to a certain value. And then as further out you go from the conductor, it's going to decay away. And you apply this equipotential electric potential on this conductor, then here it says, as what we have discussed, inside the conductor and also including the surface, we're going to have equipotential everywhere. So it's going to be a constant value, and then after that, it's going to decay, but it will decay at a smaller quantity. If you just look at the quantity here, it's going to be decaying at a smaller quantity than the electric field because it's only an inverse R relation, whereas this the inverse square R relation. All right. So we're going to take another look at another example. So electric potential due to conductors. Now we have charge 2 placed on a spherical conductor of radius 1. So we have this spherical conductor. We place the charge. And then we have another spherical conductor that has radius R2. Could be smaller or bigger, doesn't really matter. And we make them contact. Okay, so it is, or we put a very thin wire between them. They are very far apart still. So what does that mean by far apart? Meaning any field out here is not going to affect the electric charges here, the field here. It's just going to be connected, but it's going to be far apart such that the electric field outside the sphere is not going to affect the charges on the sphere itself, because if it was close together, of course, there's going to be field outward, that's going to be field outwards, and then that will somehow put these charges into another equilibrium state. But in this case, we can ignore this this problem. So as soon as we connect these two spheres together with a conductor, that means the charges will start flowing in because they can freely move, right? They can freely move. So, and what will happen is that the charges that were, the net charges that were here in R1, they're going to be, some of them are going to be moved to this another conducting sphere. And then it will also distribute along that conductor surface. Okay. So now the question is asking, after the charges on the sphere are in equilibrium, what are the electric potential on the two surfaces? Okay. So because now as soon as we connect them together, we don't have two separate conductors. We now have a single conductor, right? One single conductor, meaning the electric potential across the entire system is going to be equal. It's going to be same everywhere. So the electric potential on the surface of this, or not just the surface, but including the surface and the entire conductor, and then the electric potential in this conductor are going to be exactly the same. So V1, we can say, is equal to V2. And how do you calculate V1? On the surface, we can calculate it by applying this equation. So it's going to be Q1 divided by R1, which is on the radius there. And then for the second sphere, it's going to be Q2 divided by R2, okay? Where Q1 and Q2 are the charges that are located in the first sphere and second sphere, respectively. And Q1 plus Q2 should, of course, equal to the original charge, okay? Because it was the original charge that moved to Q2, and now the original charge is either residing in Q1, the first sphere, or the second sphere. Okay. So according to this analogy, then we can find out that we can cancel out this constant, and we can find out that the amount of charge that is in Q1 and Q2, the ratio between the two is going to be the ratio between the radius of Q1 and the radius of the first and second sphere, the ratio between the radius of the radii of the first and second sphere. All right. Any questions up to this point? Okay. Then I'll summarize this first part. This is the first part of the two chapters we are covering today. So the electric potential, of course, is the energy that is required in order to move a unit charge. So per coulomb of charge from one point to another in the presence of the electric field. Of course, when we talk about this unit charge, it has to be a very small size test charge, okay, such that it wouldn't affect the entire system. It wouldn't affect any part of the system. So in order, if we say this test charge has very small Q0, and then you want to move this from A to B under the influence of electric field. So if there's no electric field, of course, the electric potential is always 0. Under the influence of electric field, then you can use this line integral to compute the electric potential. Okay. And vice versa, from this, we can also calculate from electric potential, we can also calculate electric field, but you need to take a partial differentiation in the XYZ space. So that you can get the X, Y, and Z component of the electric field, so that you can construct your vector out of it. So you're trying to construct a vector out of a scalar quantity. That's why you need to take differentiation with respect to X, Y, and Z separate. Okay. And electric potential due to charges, many charges. For point charges, you take the sum, and for charge distribution, you take the integral. Okay, they are in fact equivalent. Where this one is just discretely adding everything together, whereas this one is continuously adding very small elements, which is the very definition of integration, right? And electric potential in a conductor is going to be same everywhere, and it is given by this equation. Okay, Ke is over Ke times Q over R, where Q is the charge in the conductor itself, and R is going to be the radius of the conductor. Right. Any comments or questions? So we can go to the next topic, which is on capacitance and dielectric. Okay, so when you have two unconnected conductors. So remember, when you connect up the conductor like that, then charges will immediately move, and then you will reach electrostatic equilibrium. When the conductors are not two conductors are not connected, and then you apply some voltage across it. You apply some electric voltage, electric potential across it. Then you're going to accumulate charge on one plate, and then the opposite charge is going to accumulate on the other side of the conductor. Okay, so that is then you can actually store some charges on these two conducting medium, and that is called a capacitance, and that device itself is called capacitor. And then the amount of the charge that the capacitor can store is called capacitance. Okay, so the capacitance is going to be given by the charge per unit potential difference. Charge that can be stored per unit potential difference is going to be the capacitance. Okay, and the capacitance itself is in a capacitor is given by the geometry, it depends on the geometry. So I'm giving you some three basic examples of how a capacitor may look like. So this is the simplest example of a capacitor, where you have a positive plate, and let's say this is a negative plate, and then keep them a distance d apart. And then if you apply, let's say, positive voltage here and negative voltage here, then of course here you're going to accumulate net positive charge on this side. Then you're going to accumulate net negative charge on this side, and then there's going to be an electric field across it. Okay, and the larger the charge, the larger the voltage you apply, the potential difference you apply, more charges will be there, and then the capacitance itself is going to be, in that case, how much charge has been drawn on each of these plates per the voltage that is applied, or the electric potential that is applied across them. Okay, that's going to be the capacitance. But from the physical construct of it, the capacitance will be given, will depend on the geometry of it, and it is given by this equation. So epsilon 0 is again the free permittivity of free space, and A is the area of the parallel plate, and it has to be the overlap area. Okay, so if the two plates are not exactly on top of each other, then you just have to use the overlap area. Calculate that, and then D is the separation between the two plates. Okay, now you can also consider coaxial cables to be a capacitor. So what's a coaxial cable? It's a cylinder. You have a cylinder, and the outside of the cylinder you have you can apply, let's say, negative charge, and then inside you have another rod inside. So all of these materials are conductors. They're conductors, and you apply, let's say, positive voltage on one of the conductors, let's say inside, and then outside you apply negative voltage. Then again, it's going to create electric field coming radially outwards from the surface of surface of the inner conductor to the inner surface of the outer conductor, right? That's going to happen, and then in this case, you can in such a construct, the capacitance is given by this equation. Okay, can also have concentric spherical shell. So inside you have a sphere, and then outside you have a spherical shell surrounding it. If both of them are conductors, then you can again construct a capacitor, and then the capacitance is going to be given by this equation. In all these three examples, the gap between the conductors, because in a capacitor you must have a gap between two conductors. The gap between conductors is just free space, meaning vacuum or air. Okay, the air there, and then these are how it is given. If you insert some medium in there, this capacitance is going to change. What about if you add another conductor in the middle? Then of course, if you add conductor in the middle and then they are in contact, then you lose the capacitance because the charge just distribute equally and then it's all gone. That will just be a conducting a single conductor, not two separate, two unconnected conductors. Okay. So when you have capacitors connected in parallel, then this is how it looks like. So you apply electric potential across the capacitance, but the two capacitors are connected in parallel. That means the charge Q comes out. So I should have written Q here. Q comes out, and then the positive charge will accumulate on the positive plate, and then the equal amount of the charge will be drawn out from this negative plate back to the voltage source, right? So that actually completes the circuit like that. But because the charge came out from this electric potential source, has to be divided into the two, either the first capacitor or the second capacitor. Then the equivalent capacitance of such a system is given by this equation, where because Q1 basically the charge coming out Q has to be divided into Q1 plus Q2, but the two capacitors connected in parallel, the voltage across them is going to be the same because they are in parallel. Then you need to when you formulate it like this, then you can say it's going to be Q1 divided by the voltage, the potential difference, and Q2 divided by the potential difference. So that says that the equivalent capacitance is going to be just C1 plus C2. Okay, so that's when capacitors are connected in parallel, the equivalent capacitance is going to be C1 plus C2. And we can easily say that in this case, then the equivalent capacitance is always going to be bigger than C1, and also it's going to be bigger than C2. What about when the capacitance is connected in series? Now the Q comes out, okay, and then it accumulates on this plate. So you have Q there. Now that draws out minus Q amount of charge from the other side of the capacitor. And then that travels along here, and then they get accumulated on this side. So this again becomes plus Q. And then that also draws out minus Q amount of charge, and then it comes back here, and then that completes the circuit. Okay. So that means, whereas the voltage, as we understand, the voltage in series, they have to be divided. So if this was V, the total V, delta V, then part of it is going to be voltage across the first capacitor, and then the remaining part is going to be the voltage across the second capacitor. So in order to get the equivalent capacitance, it has to be Q divided by delta V1 plus delta V2, okay, because that's how much charge is stored on each of these two. So the same amount of charge gets stored on both C1 and C2, and that actually is the charge that was drawn out from the potential source, the electric potential source. And when you formulate this, then it becomes that the capacitance in series is the inverse of the equivalent capacitance is the inverse of the C1 plus inverse of the C2 and plus and so on and so on. And in this case, if you do this calculation, you will always see that the equivalent capacitance is always smaller than C1 and also smaller than C2. So let's take a look at this example where we have to determine the equivalent capacitance of the combination of these systems. The 5C means 5 times that, of course. 2C is 2 times that. So in this kind of system, we can simplify the problem to just one capacitor. We can draw just one equivalent capacitor out of all this, right? And how do we do that? We first need to get the equivalent of these two capacitors in series and these two in series. So let's say the equivalent one capacitance is combining these two, then it's going to be 1 over the C equivalent 1 is going to be 1 over 5C plus 1 over C, and you rearrange everything and solve the problem, you get 5 over 6C. Then you can do the same for the second part. Then now what do you have? You have two equivalent capacitance in parallel, right? Which now I can again simplify that further. So we combine C equivalent 1 and C equivalent 2 in parallel, which means you just add them together to get the total capacitance. And then we get that, and you substitute this number in and simply the equivalent capacitance of the entire thing. So you can have so many different capacitors, or you can just simply use one capacitor that has this value, and will have exactly the same amount of charge stored in the entire system. Questions? So that should be pretty straightforward. You've done a lot of these calculations with dividing the voltage in series, and also understanding how the voltages are always the same when the circuit's connected up in parallel. So you can, this applies. You apply exactly the same thing here about using capacitance. Okay. Now, because you're accumulating positive and negative charge, and these charges cannot flow from one to another because they are not physically connected, and it creates an electric field in between, of course. Then there's going to be some energy that can be stored in that system, in such a system where you have the positive and negative charges separated, and then they still cannot flow, right? And in order to calculate the electric potential energy stored in the capacitor, you need to apply this equation. The equation itself is going to be given if you ever need them for your assessments or solving problems. So in this case, Q is the amount of charge, and C is the capacitance. And of course, knowing that C is Q over delta V, then we can substitute, instead of C, we put delta V. So then you can, that these two are equivalent. And then again, you use Q is equal to C over, C is equal to Q over delta V. Then you can again change this around. So these three equations are equivalent equations, okay, to calculate the electric potential energy that is stored in the capacitor. Okay, so when you increase the amount of charge that is stored in the capacitor, it increases the energy stored. And also, if you increase the electric potential across the capacitor, it's also going to increase the energy stored in the capacitor, according to that formula here. So we take another example. Let's say if we apply electric potential of 50 volts across A and B, how much energy is stored in this 54 microfarad capacitor? What do you first need to do? You first need to calculate the equivalent of these two. Okay? Equivalent of these two by combining the two capacitors in parallel. So these are in parallel, so how do you combine them? Just add them together. So the equivalent is going to be 90 microfarad. Okay. And then we know that this is going to give us two capacitors in series. One is going to be 70 microfarad, this one, and then another one is these two combined, which is going to be the 90 microfarad capacitor. And because these two are connected up in series, they're going to actually draw exactly the same amount of charge. So, and we can calculate that charge because we are given already the electric potential across AB, and then we know the capacitance like that. Okay. So when this Q divided by 72 microfarad is going to give us the voltage across the electric potential across the 72 microfarad capacitor, and then Q over C equivalent is going to give us the potential across voltage across the equivalent capacitance. And adding them together has to be 50 volts because that's the potential difference between A and B. And then rearranging that, and C equivalent, of course, is going to be 90 microfarad, which we calculated earlier. Rearranging that, we can calculate that 2,000 microcoulomb is going to be stored in the entire system. The charge involved in this entire system is going to be 2,000 microcoulomb. And because the voltage on the C equivalent is going to be, then we can calculate that using, you understand, the C is Q divided by the electric potential. So we can calculate the electric potential across that C equivalent C by Q dividing by C EQ. And that will give us 22.2 volts across here and here, right? That's because these are in parallel, that will be the same voltage across them. So out of the 50 volts, 27.8 volts is in this, is across this 72 microfarad capacitor, whereas the 22.2 volts is across these two. And then once you know the voltage across these two, then you can calculate the energy stored in the 54 microfarad capacitor using the equation that we have talked about earlier, the energy stored in the capacitor. Now let's talk about how the capacitance is going to be affected by having dielectrics. So before between the two conducting plates, we always had air or vacuum, in which case we were able to compute the capacitance according to their geometry, the construct geometry, for which for two parallel plates, it was epsilon 0 times A divided by D. But now if you place dielectric, means it's an insulator. Insulator is dielectric, okay? Let's talk about when you put in conductor, what will happen? Then of course the circuit is now totally connected, and then all the charges that are accumulated here will flow, and then there's not going to be, there's again going to be just a single conductor, and then all zero electric field across it, and no energy stored and no charge stored, right? But if you put dielectric, means this insulator, so still no charge can flow through it, but this can increase the capacitance of the entire system, which depends on so-called dielectric constant kappa. Okay, so this kappa is actually the dielectric constant of the material, and this depends on the material itself. Okay? It's a material dependent constant. And if kappa is kappa increases the capacitance by the factor kappa itself. Okay, so remember when we had air, it was just epsilon 0 divided by epsilon 0 times A divided by D. But now you just need to multiply kappa, which is the dielectric constant of the medium. Okay, so here is one example. A parallel plate capacitor filled with air carries a charge Q. The capacitor is connected to the battery while a slab of material with dielectric constant kappa is equal to 2 is inserted between the plates. What happens to the charge on the plate? Okay, so what we know is when kappa is 2, it will increase the capacitance by 2 times, right? So after inserting the plate, now the capacitance becomes 2 times the original capacitance times. And when you connect up the battery, when you connect up the electric potential source, the source still remains the same voltage. And that actually means what? How much? That actually means 2 times the amount of the charge now gets stored in the capacitor with the dielectric constant K kappa equals to 2 inserted into this into this space between the two capacitors. So the charge is now doubled. Is any questions or comments on this? All right. So with that, I think I will quickly summarize the second part of the summary lecture, which is on capacitance and dielectrics. So capacitance is defined as the charge stored per electric potential, the voltage of electric potential. And it is constructed by having two conductors that are separated distance d apart. And you apply voltage across it, and then it will, of course, accumulate some charge on these two plates. And when the capacitors are connected in parallel, you just simply add them together. Whereas if they are connected in series, you have to take the inverse and then add them together, and that will give you the inverse of the equivalent capacitance. And the energy stored in the capacitor is given by this equation. And then if you add dielectric medium in the place between the two conducting plates in the capacitor, you can increase the capacitance by the amount that corresponds to the dielectric constant kappa. Right. So that ends the summary lecture today. If you have questions or comments, you may remain and ask. If not, then next week we have recess, so no summary lecture next week. But then after that, in week 8, we will continue with the magnetism part of this part 2. So I think I will now stop recording. Thank you very much for attending.